Let's go ahead and get started. I have the pleasure again to introduce Mohammed Mhanna. He will give us another session today about data extraction and data analysis. This is follow-up for his talk yesterday. Mohammed, you can take it from here.
Thank you again, Dr. Turek, and thank you guys for having me here today. So as yesterday we finished with our first part of the series, the second series of the lectures to how to conduct a systematic review and meta-analysis. We were done with databases screening and and search, and now we are at the point of having our included studies ready for the next phase of systematic review and meta-analysis performance. So the objectives of today's study will be focused on how to extract data. We will start with qualitative data extraction, and then we will move forward for quantitative data extraction. And then we will learn how to do quality assessment and risk of bias assessment for the included studies. And finally, we will give a mini introduction to data analysis. Okay, so just a refresh for the types of data that we have. So there are two main types of data that we have, either qualitative data, which include nominal and ordinal data, and quantitative data, which include discrete and continuous data. For meta-analysis, we are interested in two types of data. As I said, continuous data and like age, weight, height, body mass index. And for a group of individuals, these data usually represented as a mean and standard deviation, or with a median and interquartile range. Even for categorical data or nominal data, like gender or disease status, for example, diabetes, no diabetes, heart failure, no heart failure. For a group of individuals, also we can represent this as an events in relation to the total population or as a percentage. For example, if we have a group of patients, 100 patients, 50 of them were males. So for this group of individuals, 50% of this total population were males. Okay, so let's start with qualitative data extraction. And most of the meta-analysis will include a table, and usually this is the first table in the meta-analysis that describes the baseline characteristics of the studies. So for example, the reviewers and the readers, they need to know more about the data, the studies that you included. So you will give them this nice table, the focus table that summarizes the baseline characteristics of your included studies. And most of the times we include, in this table, we include the study, we name the study, and then we state the origin and the study design, the sample size of each included study, and in their inclusion criteria, if they are different, if the inclusion criteria were different among the included studies. And for sure, the follow-up duration and primary and secondary endpoints for each study. And for sure, you can adjust these items based on your research. So if you feel that you have to report something important in the study characteristics, you may add more, and you can adjust your table based on your research. So as I said, most of the published meta-analysis will represent these characteristics in their first table. And this table should look like something like this. So this is table one, and this is the table one from our meta-analysis that we discussed yesterday. So you will have multiple columns, and then you will have rows. The first thing, the study, the first column, you will name your study. The included studies. So we ended up yesterday, if you remember, we had 10 included studies, and you name them most of the times, you name them based on the last name or the first author. For example, here is Dalan, and then the year of publication. So your study, you will name it Dalan, 2021, and you do the same for the rest of your studies. The second column, it will be or the origin or the study design. So this study was originated from Brazil and was single center study. And the second study was multinational, multicentric study. Because all of our studies here were randomized controlled trial, there is no need to mention the design, because we know that all of our included studies were randomized controlled trials. But for example, in case you had more than one study design in your included studies, you may need to report them here. For example, the origin Brazil and the study design RCT, or the origin like multinational and the study design was prospective cohort study. So, you know, the readers, they can have some insight about your included studies. And the third column here will be the sample size, and you can do the total sample size. For example, in this study, the first one, Dalan 2021, they included 50 patients. 35 of them were in the therapeutic hypothermia arm, while 15 patients were in the standard of care arm. And you do the same for the rest of your studies. And here, what I said, if you can adjust your table based on your research question, because here it's very important for us to report the method of cooling or the method of hypothermia utilized by every study, because we can, this is very essential, and you may need to do, sometimes you need to do subgroup analysis based on the type of the intervention. So here we stated that the method of cooling was endovascular cooling here, peritoneal cooling here, service, intracoronary, etc. And again, back to the usual baseline characteristics of the studies, the follow-up time, which is very important. Here was like 30 days, etc., 180 days. And then the primary endpoints, secondary endpoints for each study. And again, here we were interested in measure adverse cardiac events. And you have to state here, for example, what were the specific endpoints for major cardiac adverse events in each study. So here the measure adverse cardiac events were death, recurrent myocardial infarction, and target vessel revascularization for the first study. And you do the same for every single included study. So for table 1, please keep it focused, but at the same time keep it informative. And please avoid writing down long paragraphs or sentences. You need to make your table eye-catchy. You know, it should be easy to be read, and but again, it should be informative. And you can apply abbreviations as much as you need. For example, here, to make it more focused and more informative, you don't need to type down target vessel revascularization. You don't need to type like myocardial infarction, because it will give a lot of size to the table. You can just type the abbreviation, and you can here down at the bottom of the table, you can add abbreviations list and state what TVR stands for or what MI stands for. So by doing this, you keep the table focused, but also informative. Okay, there is a second part of qualitative data extraction, which is to assess the quality of each study, and we will discuss this later. But before doing that, before you were able to do that, you need to know more about your studies. So probably the order of your steps should be extraction of the baseline characteristics of your studies, and then move forward to extract the data, the quantitative data, so you can have an idea of your studies. And then the last step gonna be assessment of the quality of each study. So for quantitative data extraction, you need to extract the baseline characteristics for your included patients, and then you need to extract your main study outcomes data. So for baseline characteristics, so most of the meta-analysis, they will include baseline characteristics of their included patients in a separate table, and it's usually table number 2 in the main manuscript. And the first thing you have to do is to extract the data from each study for the baseline characteristics. And then you may need to combine these data into a single group, so you have your own numbers for your own meta-analysis. And then if there is any discrepancy between the statistical tools used in between the included studies, you may need to unify that. For example, if 9 of the included studies mentioned reported age as a mean and standard deviation, while one of the studies reported the age as a median and interquartile range. So to make it easy on yourself and on the readers, you may need to convert the median to the mean and standard deviation. And we will discuss this in a little bit. And you can do an extra step, and actually I did this extra step in every single meta-analysis. I test the homogeneity of the included patients in terms of their baseline characteristics. Because for me, it's very important to test this because this could be like the differences in the baseline characteristics. They could actually introduce some bias or some confounders in your meta-analysis results. So as I said, the baseline characteristics, most of the times they include age, gender, body mass index, and the baseline comorbid conditions like diabetes, hypertension, or heart failure. And again, you can add other characteristics as you need it based on your research question. So let's see how we do this. So I do this using Excel, and I use an Excel sheet. I start typing down the names of the studies in the first column. I start extracting the baseline characteristics. The first thing that I do is to extract the age. And here, as you can see, I divide each characteristic into 2 groups. The first group is the intervention group, the therapeutic hypothermic group in our case, and the second group is the comparator group or the control group, in this case, the standard of care group. So now we have columns for every single outcome in our baseline characteristics. For example, here, the age, we need to extract the mean for the therapeutic hypothermic group, the standard deviation for the TH group, and then the total number of patients included in the TH group. And the same we do for the control group. We extract the mean, standard deviation, and the number of patients. And this has to be done for every single included study. And again, if this is for continuous data, age, and we do the same for categorical data or nominal data. For example, here, the gender, we extract the number of males in the therapeutic hypothermic group, the total number of patients in the TH group, and the number of males in the standard of care, and the total number of patients in the standard of care for each single study. So let's say that we have 3 studies here. I named them, Mohammed, Aziz, and Hazem. So you go back to your papers, the included studies, and you extract the data for every single baseline characteristic. Okay, so this is the formula that I use. I think it's practical, and it allows you to export your data in a clean fashion. Okay. Okay, so here I will show you how this Excel sheet should look like after you end up extracting all of your baseline characteristics. For example, here you have a file with all of your included studies, Dallin, Dixon, El-Farisi, and etc. The 10 included studies. I suggest that you order them in alphabetical manner from A to Z. So you have, and the same order you apply to your Excel sheet, the same order you apply to your RevMan, the meta-analysis program that you use, so you don't mix up the numbers. So keep it in the same order from the start. So here we go through this study, the first one, and most of the clinical trials or the any observational studies, they will include their baseline characteristics of the included patients in table 1. So as you can appreciate here, the average age for the hypothermic group was 59 with a standard deviation of 9.3. And for the control group was 55.5 with a standard deviation of 11.2. And the total number of patients in the hypothermic group was 35 and 15 for the control group. So what you have to do, you have to just export these data into your Excel sheet. And I will show you how. So this is 59. It goes to the second column under the hypothermic group, age, mean. Here, 59. You have just to export this number here under the mean of the therapeutic hypothermia group under the age characteristic. And the same for the standard deviation, the same for the number, and you do the same for the other group, the standard of care group, 55.5, 11.2, and the number 15. And you do the same for the second study. For example, here's the second study, Dixon, 2002. Most of the times, as I said, they will represent their baseline characteristics for their included patients in table 1. And here is the age 52 plus 9, plus minus 9, standard deviation of 9 in the TH group, and 58 with 18 plus standard deviation in the control group. And you then have to report the number of patients in each group. Okay, so now we have the mean standard deviation number in the TH group and the mean standard deviation number and the standard of care group for the age. And you do the same for all of your included studies. And then you move to the next baseline character. For example, here the gender. So males, you go again for your studies. Here, there were like 28 males in the TH group from 35 total patients, and you have 11 males in the standard of care group. And here is they reported women, so it's easy. You subtract the total number and you will have your males number and etc. So then you do the same for the rest of your baseline characteristic. And if you face this situation, as I said, when you need to convert your median to mean, there is a well-established statistical methodology described by Leo and his colleagues on how to convert the median to the mean and standard deviation for a group of patients or for a group of population. And actually, there are many online tools that help you to do so. I use this website to convert the median to mean and standard deviation. So here, for example, this study by Erling et al., they reported the age as a median and standard and interquartile range. And you know this by looking into the bottom part of their table. And they say that the values are median and range. So this is not the mean, this is the median. And this is very important to recognize because you cannot combine mean and median. You have to convert the median into the mean to be able to combine the data from several studies. So it's easy. This is the median, the first interquartile range, the third interquartile range, and you have the number, it's 61. Then you go to this online tool and you type in the size of the sample. It was 61. The first quartile range was 37. The median was 57, and the third quartile range was 79. Then you calculate, and then you have your mean and standard deviation. So the mean here was 57.7, and the standard deviation was 31.8. And then you just report these numbers into your Excel sheet. Okay, so now we solved this problem. We fixed it by converting the median into mean when you need to do so. And this is what it should look, that your final Excel sheet should look like, something like this. For age, you extract all the numbers for each group from each study, for gender, for hypertension, diabetes, and all of your baseline characteristics. Okay, this is actually an extra step that I prefer to do, because it actually gives me and gives the reviewers and the readers an idea about your study population, because now you came up with new numbers. You combine the data from several included studies, so probably you have new numbers, and you need to know how homogeneous is the two groups of your meta-analysis. So this is another online tool that I use, and it actually combined the mean and standard deviation from different groups into one single group. And this is the whole idea about doing a meta-analysis, is to combine the data from several studies into one group, so you can investigate, you can study the pooled effect size. And I like to do this with the baseline characteristics, because, as I said, it's very crucial to know if there is any baseline differences between your two groups. For example, in our situation, we are interested in testing hypothermia effect in STEMI patient, but what if the therapeutic hypothermia group, the age they were older, or if they had any more baseline comorbidities? For example, if they had more heart failure, or if they had more diabetes than the control group. So this is a problem, and it's not a problem, but you have to mention this and you have to report this, because if this is the situation, you may need to do an extra statistical step to do a meta-regression to see if the age, for example, had any effect on your outcomes. So it's better to know from the start if you have any differences in your baseline characteristics of the included patients. So it's simple. I add, so here for combination of your data, I just add another row for total numbers. So just for the continuous data, you just copy and paste your total number, the mean and the standard deviation, and these are the values for the age, in your treatment group from all of your included studies. And you just copy and paste your values into your online tool. And this is designed where you have to put the sample size in the first column, and the mean in the second column, and the standard deviation in the third column. So that's why I rearrange the data here to have the numbers here, the mean here, and the standard deviation in the third column. So when I copy and paste, they have the same order as it is requested here. So now you can see that we combined the mean and standard deviation for the age in the therapeutic hypothermia group for all of your included studies. So the total number of patients, now you have 364 with 58.6 mean and probably 16.5 standard deviation. So now you know that the mean age for all of your patients under the therapeutic hypothermia group was 58.7 plus minus 16.5. And actually you do the same for the standard of care group. So now you copy and paste your values here. So you know that the standard deviation, the mean value for the age was 58.7, standard deviation of 16.5, and your total number of patients in the therapeutic hypothermia group was 364. And actually you do the same for the standard of care group, for your second arm, for your other group. You just copy and paste, rearrange the data, copy and paste them, and then you will have your combined mean and standard deviation. Okay. Again, you repeat these steps until you are finished with combination of all of your baseline characteristics. If you want to do more, so this is for continuous data like age, body mass index, height, etc. For nominal data or categorical data, you may use the function in the Excel sheet, the function of sum. You type equal, and then you choose sum, and then you pick up all of your columns, and just then press enter, click enter, and then you will have all of your numbers here. So for example, here under the gender male, you have 301 males out of 364 patients in the therapeutic hypothermia group, and you have 276 males out from 342 males under the control group. So these are your own numbers, the numbers of your own meta-analysis, right? If you want to do an extra step, you can always combine these numbers so you have the total numbers of your patients. For example, here, the total numbers of your population was 706 with a mean of 58.4, standard deviation of 17.3. And here you had 577 males out from 706 total patients. And this is when you are done with extracting and combining all of your baseline characteristics. Okay, so as we said, now we have our numbers for each group, for each baseline baseline characteristics. So you have the mean and standard deviation for the age, for example, for the TH group, and the mean standard deviation, the numbers in the therapeutic, in the standard of care group. And now you may need to test if there's any difference, if there is any difference in between your two groups in terms of their baseline characteristic. And you can do it with Revman. And actually, this is the review manager. This is one of the program that we use to run our meta-analysis, our main analysis. But you will learn more about this with Aziz in the last two lectures. So don't worry if you don't get it today, how to conduct an analysis in Revman, because we will do this again with Aziz. But just I wanted to show you how we can test the homogeneity of your baseline characteristics in your included patients. You just open Revman, and don't worry about all of these steps. You will learn more about them in the last two lectures. You open the program, you add your studies here at the references, you add them one by one. So you just copy and paste the studies and you add them. As I said, don't worry about all of these steps, but I wanted to show you how we can test if our baseline characteristics were homogeneous. Don't worry about all of this. We will learn more about this. So after you're done with adding all of your studies, you may need to run a small analysis. Again, don't worry about all of these steps. So after you're done with adding of all of your studies here, you will end up and you will know how to do this in more details with Aziz. But you will know how to reach to this point. So simply here we are testing if the age was different in between your two groups. You just copy and paste all of your numbers here, and then you can see that the p-value, which is the difference, there was no significant difference in between the baseline age in between the two groups. So the therapeutic hypothermia group and the standard of care group, they had a comparable age. So the p-value was not significant and the heterogeneity was not significant. So you can see in confidence that the age in between the two groups was not different. And you can do this for all of your baseline characteristics. And if you want to do this for for categorical data, like for gender or for males, you can do the same steps with the gender. And just copy and paste your values here, event totals, and then you run the analysis, and then you can see that it was not significantly males. The percentage of males in the two groups were what was comparable. Okay, so as I said, most of the meta-analysis, they will represent their baseline characteristics in table 2. And this how it should look like after you're done with extracting all of your data. So here, age, male, body mass index, baseline comorbidities, hypertension, diabetes, etc. And here is very important for us to report how many patients had anterior STEMI, inferior STEMI, what is the TIMI flow, etc. This can be adjusted. This can be adjusted, as I said, based on your research question. And the second column here, number of studies that reported this outcome. I'm sorry, not outcome. This baseline characteristic. So, for example, 10 out of 10 of included studies, they included the age, which does make sense. But, for example, here, the body mass index was reported only in 5 studies. And these are the values for all of your patients. So you had 706 patients in total, and the mean age was 58.6 with a standard deviation of 17.4. So now anyone can read easily through this table and know. So for example, the mean age for your study was 58.6 plus minus 17.4. And for the TH group, the age was, for the total group, the mean age was 58.7 with 16.6 standard deviation. And here, 58.4 with 18.3 standard deviation for the standard of care. And as we tested this before, there was no significant difference in between the two groups. So you can say in confidence that these two groups had a comparable age. And the same you do for the rest of your characteristics. So here we had 81.7% of our population were males. 82.7 were males in the TH group. 80.7 were males in the standard of care group. And males numbers or the percentage did not differ significantly in between the two groups. And you do this for the rest of your studies. The rest of your baseline characteristics. So as is stated in the Cochrane guideline for conducting systematic review and meta-analysis, the data extraction should be performed by at least 2 independent reviewers, so we can avoid any human error. Okay, so now we can move to the next phase of quality assessment or qualitative data extraction, which is a quality assessment and risk of bias. And this has to be done in every single meta-analysis, because you want to know if there is any risk of bias in any of your included studies, because the level of confidence that you say that your outcomes, for example, favors the intervention A in comparison to intervention B is actually driven by your included studies. And if there is any risk of bias in your included studies, then the risk of bias will just be transferred to your results. So you have to actually to test if there is the quality of your included studies. And there are many tools available for quality assessment, and depending on the design of your study, of your included studies. So for example, if your included study was a randomized controlled trial, you need to use ROP2. And if it was an observational study, you use NIH tool. And the same for non-randomized trials, you use Robbins 1. And if you are dealing with case reports, you can use the CARE tool. Okay, what do I use? I actually prefer using the Jaddad composite scale for the randomized controlled trials, for quality assessment of randomized controlled trials. The scale is actually range from 0 to 5 points, and any study with a total score of 3 or more, it is considered to have a low risk of bias. And for observational studies, I use the Newcastle Ottawa Quality Assessment Scale, and it actually based on 4 parameters. The selection of the study, 3 parameters: the selection of the study, the comparability, and ascertainment of the exposure and outcomes. And any study with a total score of 6 or more is considered to have a low risk of bias. This is the questionnaire that is used by the NIH tool for case control or for cohort studies. I cannot see it. Probably this is for cohort studies. So here is the 3 main items. The selection, you will assess each study, the risk of bias in each study based on their selection methodology, the comparability, and the outcome. And there are 4 sub-items under selection. The first one is the representativeness of the exposed cohort, and the selection of the non-exposed cohort, the ascertainment of the exposure, and the demonstration that the outcome of interest was not present at the start of the study. And then you move to the next item, the comparability, and to see if the two groups were comparable or not. And if the study they controlled for important factors in their design or their analysis. And the last item is the outcome. And there are 3 sub-items here: the assessment of the outcome, and was the follow-up long enough for the outcomes to happen, and the adequacy of the follow-up of the cohort. So each item here can gain 1 star. So 1 here, 1 here, 1 here, or no, if you feel that this study doesn't meet every single item here. And then the comparability, they can get 2 stars from, any study can get 2 stars from the comparability. And again, the outcome, 1 star for each item. As I said, any study with 6 or more stars or points, they consider to have low risk of bias. And this is for case control observational study. The same concepts are applied here: selection, comparability, and the exposure. 1 point for each item, 2 points here, and 1 point for 1 point each for the exposure. Any study with 6 or more, low risk of bias. So because these slides were, I think they were busy, I just broke them down here. So for case control, 4 points; for selection, 4 items and the selection, and each item can have 1 star or 1 point. Here, one item in the comparability, but you can give 2 stars here, or 2 points if the study meets the comparability section. And 3 items here with 3 stars. So as we said, a study can be awarded a maximum of 1 star for each numbered item with the selection and exposure, but 2 stars for the comparability. So let's navigate through this questionnaire, or this tool, to assess the quality of your included studies. So here, for example, is the case, you have to ask yourself this question: is the case definition adequate or not? And if yes, if you believe that the case definition was adequate, for example, if the definition of the case, in our case, if let's say this was not a randomized controlled trial, this was like an observational study, and if they define the cases as STEMI patients based on the EKG, for example, then the case definition was adequate, right? So you give this study a star for this item. And again, the same you do for the second item, the third item. So for example, selection of controls, if the controls were selected from community, then you give them a star. If just from hospitals or there was no description of the methodology of the control selection, you don't give them a point for this item. Here again, say that they describe the cases just based on the ICD codes or based on self-report. So now you cannot give a star or a point for this study for this item. And again, the comparability, as I said, you can give 2 points for comparability. And if you feel that the study controlled for important factors like age and baseline comorbidities, either during their study design or during their analysis, you can give them 2 stars for comparability. If you believe they don't or they meet only 1, you give them 1 star. If none, you give them 0 stars. And this is for the exposure again. And this is for cohort studies. And so this is important in cohort studies. The last point of the selection items is to do if the study demonstrated that the outcome of interest was not present at the start. And in case of mortality studies, the outcome of interest is still present if the disease or the incident rather than the death. Even if a death happened, you still need to report the incidence or the disease itself. Okay, so this is after you're done screening all of your included studies for quality assessment, you end up with this table. And this table for randomized controlled trial, the JADAD scale for quality assessment in randomized controlled trial. So we have 3 main items. You assess the quality based on randomization, blinding methodology, and withdrawal from the study. And under randomization, if the study was described as randomized, you give them 1 point. If you feel that randomization was appropriate, you give another point here. And for blinding, if the study was a double-blind study, you give them 1 point. And again, if you feel that the blinding methodology was appropriate, you give them another point. And here's the attrition bias or the withdrawal or the dropout part. So each study, each special randomized control study, they have to report the dropout and the reason behind the dropout from the study. Again, if you believe that the study reported well the dropout numbers and the reasons behind the dropout, you give them another 1 point. So the total number of points here randomized control on the JADAD scale, the total number is 5, 1 for each item. Okay, so there is a lot of background noise. If you can just mute your microphones. Okay, so here's the final score here. So this study, it gained 3 points. And as we said, according to JADAD scale, any study with 3 or more points, they consider to have low risk of bias. So this study, for example, it gained only 2. So it has a moderate risk of bias. And this is for observational studies. As we said, you screen the studies based on selection, comparability, and outcomes, and you have sub-items under each one. So 4 items here, 1 item under comparability, and 3 items under the outcomes. And you can give 1 for each item here, up to 2 for comparability, and 1 for each item under the outcomes. So you will end up with 9. So a study with 6 or more points under the quality score, it's considered to have low risk of bias. Okay, so now we are done with base studies, characteristics, extraction, table 1. We're done with baseline characteristics. We learned how to combine the baseline characteristics to have your own data to compare the baseline characteristics between the two groups of your population. Now, and we are done with the quality assessment of your included studies. And now it's the time for the analysis part of the meta-analysis. So it's the time for data extraction for your outcomes. So for example, here, so again, if your outcome is a continuous data, like for example, you're interested in left ventricular ejection fraction, LVEF percentage, this is a continuous data. And you have to extract the data, as I said, in mean and standard deviation, and you can convert the median to the mean as you need. And for nominal data, for example, if you are interested in mortality, you extract the number of events in each group in relation to the sample size. And again, this step has to be done by 2 independent reviewers just to avoid the human error in data extraction. Okay, let's move forward. So again, I use Excel sheet. I open a new one for study outcomes here. The first column for the study names. And again, they are in the same order during all our phases of data extraction, so you don't mix up the studies and the numbers. So for example, here, we are interested in all-cause mortality. Okay, so we put 2 groups, our treatment group, the TH group, and our other group, the control group, the standard of care group. And then we put another column for the events and the total number of patients, events and total number of patients. And we go through each study and we extract the data. Sometimes the data are not well represented in a nice table like table 1 for the baseline characteristics. Sometimes these data are hidden through the manuscript. So sometimes not easy to get these numbers. You need to read in depth and to read every single detail and your included studies so you can retrieve these data. So for example, here with the first study done 2021, they had 1 event, 1 mortality, 1 patient died out of 35 in the therapeutic hypothermia group. And here they had 1 patient died in the out from 15 in the control group, in the standard of care. And then you do the same for all of your studies. So here 0 patients died in 21 out of 21, 2 patients died out of 21, 0 out of 50. Here 4 patients died out of 58 in the treatment group, 0 patient died out of 53 in the control group. And here, this is for categorical data or nominal data. Remember, event total. For continuous data, again, as we did in the baseline characteristics data extraction, you extract the mean, standard deviation, total number of patients in the treatment group, and then you extract the mean, standard deviation, total number of patients in the control group for every single study that you included in your meta-analysis. So here, the infarct size was 13.9, standard deviation of 8, and the total number of patients were 35. This is in comparison 13.8, 10.8 standard deviation, 15 patients in the control group. And then you just continue these steps for every single study that you include. So can we pool the data as we did in the baseline characteristics? Can we just pull the numbers for the outcomes for your main outcomes. Actually, you cannot do that. You cannot just say here that we had 1, 2, 3, 7, and 10 deaths and the total in the therapeutic hypothermia group out of these numbers, because it doesn't this is not the meta-analysis idea. So the meta-analysis idea, it is interested, we are interested to see the pooled effect size, or the effect of the total effect deriving from all of the included meta-analysis. But put in mind that not all of the studies were the same. So for example, this study, it contained around like 120 patients, while this study, it only contained 18 patients. So you cannot combine the data from the two studies without putting the weight of the study in your consideration. So the meta-analysis, yes, it does pull the effect from many meta-analysis, many included studies, but it takes into consideration the weight of each study. In other words, the amount of contribution to the final pooled effect. And usually the main effect, it usually represented as either odds ratio, risk ratio, or hazard ratio for categorical data. For example, mortality, disease status, and the mean difference or the standard mean difference for the continuous data. And again, you're going to learn how to do the analysis and how to get this first plot for the mean effect. So for example, here, just don't worry about how you can do this. You will learn about this. But for example, here we had our included studies. Here we are testing the mean difference for the infarct size, for example, okay? So we had 217 patients here, 196 patients in the control group, and the mean difference was negative 0.87, and the mean difference was not significantly different in between the two groups. But look here, this is the weight of each study that contributed to the final pooled effect. So 25%, almost 1/4 of our study effect, it was driven from Nicole 2015 study. So this weight should be considered when you are doing your meta-analysis. And why I'm saying that, because this is very important when you are reporting the publication bias. And we will come to this in a short minute. Okay, this is again for categorical data. For example, mortality, you have these events, the total events total for each of your groups. And then again, around 40% of your pooled effect, it came from Dalan 2021. Okay, why it's important to recognize the weight of each study? Because this is also related to publication bias. So what is publication bias? Publication bias, we know that studies with positive outcomes are more likely to be published. And we know that studies published in English or written in English are again, they are more likely to be published, while negative studies are less likely to be represented or published. Thus, in a meta-analysis, it's likely that more positive studies are represented in your meta-analysis and less negative studies. For example, if a study had negative outcomes, it is less likely to be published, and it's less likely to be represented in your meta-analysis. And this actually could give a publication bias in many of the meta-analysis. It's nothing to do with your methodology of databases researching or extraction, but it's the way that publication happened. As I said, studies with positive results, they are more likely to be published than studies with negative results. And how we can assess for publication bias? we can actually assess for publication bias either subjectively or objectively. So subjectively, you can visually assess publication bias from the funnel plot. But you have also to do objective assessment with many of statistical tools. The most commonly used one is called Eager's test. And this is the funnel plot, and actually you have to do this in your meta-analysis. Some studies, some guidelines, they say that you have to do funnel plot if you have 8 or more included studies. Some of them, they stated that you have to do funnel plot if you have 5 or more included studies. But what we usually do the funnel plot when I usually do this if I have 5 or more. So you don't have to do funnel plot if it is below than 5, if your included studies are below than 5, because it doesn't make any sense to do publication because you only have less than 5 studies included in your meta-analysis. So let's talk a little bit about the funnel plot. So in the past, they used to do the funnel plot. The x-axis is the mean effect size, and the y-axis is the study size or its variance. So by doing this, large studies, big studies, studies with big weight in your meta-analysis, as we discussed, usually they will be distributed in the upper part of this graph. And they will be around the mean effect. So this is the mean effect or the pooled effect of your meta-analysis. So the big studies, they would be represented here because they are contributed more to your mean effect size. While smaller studies, they will be distributed here, down here, and far away from your mean effect. So this pattern of distribution, high, near to the mean effect size for big studies, down to here, peripherally, and away from the mean effect size for the small studies, it actually resembles a funnel. So that's why this plot, it's called the funnel plot. But they then they did some modification on the funnel plot. Instead of putting like the mean effect size, they put the log odds ratio or the log hazard ratio or the whatever statistical tool, the log of the statistical tool that you use in your meta-analysis. And instead of putting the sample size or the variance, they put the standard error. And why they did this? It actually helped with spreading out the small studies at the bottom of the graph. So you will have your small studies here distributed more, and it doesn't have anything to do with the statistics. It does just change the distribution of the small studies, so you can actually visualize funnel plot in a clearer way, so you can see the studies distributed apart from each others. So by doing this, for example, in this situation, we can, and I don't know if you can see that this part of the funnel plot, it's lacking any studies here. And if you think about it, so you are missing probably a large size study here that has a positive impact of your outcome, which is mortality. So in other words, you may be missing a large study that showed more mortality or more negative outcome, right? Because here we are studying mortality here. This funnel plot is for mortality. So positive means positive number. It means the negative in the outcome here for mortality. It's worse to have more positive in mortality. So probably we are missing big study with negative outcomes, and that is the concept behind the publication bias. as we mentioned, that negative studies are less likely to be published. So as we said, by visually inspecting this funnel plot, there's asymmetry in the distribution of the studies around the mean effect size. And probably we are missing studies in the right upper part of the funnel plot. But as I said, this is just a subjective estimation of the publication bias. And you have to do objective estimation by running a statistical analysis. One of them, the most commonly one actually used, is, as we said, is the Eagers test. So the Eagers test, it's the regression of the effect size on its standard error weighted by its inverse variance. The actual steps is very complicated, but thanks God we have a lot of programs that can calculate Eagers test for us. And you need to know this, just only need, you have to know this. If the p-value of the test, of the Eagers test, was more than 0.05, there is no risk of publication bias, even if your funnel plot is asymmetrical. As we said, this funnel plot, just the inspection is a subjective way, but the objective one is to run an Eagers test. Okay, so if the p-value of the test was above 0.05, you don't have publication bias. So what if your p-value is less than 0.5? Then you probably have a publication bias. So what we have to do, if we are sure if the p-value is less than 0.05, we're sure that there is a publication bias. So how we can adjust for the missing the studies that we are missing from our analysis. As I said, it doesn't have anything to do with the screening phase, but this is the nature of publication. Publication bias is something inherited, you know, you cannot do anything for it. But we can do something statistically wise. We can adjust or provide an effect, summary effect, adjusted for this publication bias. And I will show you how. So there are many methodological, statistical methodological tools that can actually adjust for the publication bias. The one that's most commonly used is what's called trim and fill method. So trim and fill method, it will calculate how many studies you are missing. For example, 2 studies at the side of the negative outcomes, or 2 studies at the side of the positive outcome. And the program, it will run an analysis for you that will give you the mean effect, but it is adjusted for this publication by adjusted after adding these 2 or 3 or 4, whatever studies. And to do this, the Revman or the review manager, the most commonly used program for meta-analysis, that cannot do the Eagers test. So there is another program that is called Comprehensive Meta-Analysis, or CMA, that gives you the Eagers test, the p-value of the Eagers test, and it will do the trim and fill methodology to adjust for publication bias if any exists. Let's see. Okay, this is the CMA, and again, you will learn more with Aziz, and I'm sure that it will be an interesting lecture with data analysis with Aziz, so please don't miss it. Okay, so first you open the CMA, and you insert a column for study names. And here it's easier than Revman because you can just copy and paste all of your studies all at once. Then you insert, let's go back, you go to column, insert column for effect size data. And here, I'm sorry. Let's go back. Okay, so insert column, effect size data. Here is it, column effect size data. And here we are interested in comparison of two groups, right? So you click this, and then you go to whatever statistical tool that you are using. And again, you will learn about this more. Don't worry about all of these steps. Then now we have two groups, group 1, TH, group 2, standard of care. And here the event total number, events total number. And then if we are interested in mortality, just copy and paste all of your numbers, and then you run your meta-analysis. Don't worry about all of these. This is the actual forest plot that you will learn more about with Aziz. But here I just want to show you the publication bias. You cannot actually do the publication bias without doing the meta-analysis itself. That's why I'm showing you this. So here, so after you're done with your core analysis for your mean effect, you go to analysis, and then you go publication bias, and here's it. So this is your funnel plot. It's the same the same as the one that I showed you earlier. So we have 4 studies here at the left of the graph, 2 studies here. Probably we are missing 1 or 2 studies objectively by just inspection in the right upper part. But again, this is subjective, right? Now we go to tables. Now we go to table. There, as I said, there are many statistical tools that can assess the funnel plot. And here we are interested in Eagers test, and you can appreciate the p-value. If your study is two-tailed, it is 0.5. So 0.5, what does it mean? There is no publication bias. If you have a publication bias and the p-value of the Eagers test was less than 0.05, then you move to the next step. You move to the next step. Okay, next table, and then you will find the trim and fill methodology that can adjust for your publication bias. So here they provide 2 outcomes, right? So your mean effect here, 0.76, for example, your risk ratio or odds ratio for your outcome was 0.76, and upper limit, the confidence interval, upper limit, lower limit, and your p-value. If you have a publication bias, the program itself will adjust for it. So it will add 2, 3, 4, 5 studies here. Okay, now we don't have any publication bias. That's why it didn't add anything, because you don't have to adjust, as you don't have publication bias. But say if we have publication bias, it will add number of studies here, and it will add, you will tell the program that I am missing studies to the left of the mean or to the right of the mean. Okay, to the right of the funnel plot, as we discussed, or to the left in some cases. And if you are doing the study under the analysis under random effect, and we will come again in the last 2 lectures, what is random effect, you have to keep the same methodology as your initial analysis. So you do it under random effect. Now the program, it will give you a point estimate adjusted for your publication bias, or adjusted with addition of 2 or 3 studies. Okay, and actually you have to report this in your paper, in your manuscript, that after you adjusted for publication bias with the trim and fill, the point estimate was 0.9 instead of 0.7. And if the 2 values are pretty different, this is problem, because probably this publication bias affected the main outcome of your study. And this is how you should report the quality assessment and bias assessment on your final manuscript. you will say that the quality assessment of the RCTs are summarized as we showed you in the tables, and you have to put these tables as supplementary tables, and you will say that, for example, most of the studies scored low to moderate in quality assessment, and again for publication bias, you will say the funnel plot for your outcomes shows some asymmetry by visual inspection, but the Eagers regression analysis did not show an evidence of publication bias because the p-value was, for example, 0.08 for this outcome. Okay, I think I'm done. Thank you so much, and if you have any questions, please let me know.
Thank you, Mohammed. That was really fantastic. Let me ask you a question. After doing several meta-analysis, how hard it is to do meta-analysis?
The first one, it was hard, to be honest, because you don't know the steps, and you have to be very precise, when you extract the data. So it was hard, especially, but when you do more, things become easier.
Exactly.
For example, like the first one, probably it took us like a month to do. Now we can do a full manuscript in a week or so.
Yes, this is my observation.
Yes.
I have a question. So when you are evaluating the quality of the studies, I think using Jaddad score, if it's more than 3, then this is good quality study.
Yes.
But one of the studies that you showed, Nichols 2015,
yes,
score was 2, yet the effect size when you did the meta-analysis was the highest, 25%. What do you do in that case? Do you exclude that study, or how to adjust for that?
Yeah, good question, Dr. Turek. Actually, you don't have to exclude the study as long as it's low to moderate risk of quality. If it's moderate risk, you can accept it. But if it's a high risk of bias, you have to expand more in your discussion. What harmed the quality of this study? Which the good observation, yes, that it contributed 25% of your outcome weight. So you have to discuss more. You don't have to exclude it actually, but you have to describe why you consider this as high risk of bias or low quality. But no, you don't have to exclude it.
Okay. And looking at the variables that you are evaluating in the meta-analysis, how do you decide on these variables? Do you combine all patient characteristics reported in the different studies? For example, I saw you looked at the buspirone, but yet not all studies will report that. How do you decide what variables you look at?
It depends. It depends on your research question. For example, here I think we have to know how many, because this is therapeutic hypothermia. We have to know how many patients they were given buspirone for the adverse effect of hypothermia. So I know that not all of the studies reported this, but at least we report in our table how many studies they reported the use of buspirone. For example, 80 studies here, they reported the buspirone. So for the baseline characteristics, you don't have to have, all of the studies of the included studies reported this specific baseline character. But if there's 5 or more studies or more than half of your included studies reported this baseline character, you may need to report it because probably it is important.
Okay, excellent. And now looking at the chat, there's a question from Umayma. What do we exactly mean by event?
Events, number of events in total. For example, if we are interested in mortality. So say we have in our intervention group 50 patients, 50. So the population of the intervention group, the number was 50. And we have 5 patients died in that group. So we have 5 events in the total of 50. So you have 5 events, the total number is 50. And you do this the same for the control group. You have 2 events, 2 mortalities in a group of 20 patients. And this is only for nominal data, for categorical data.
Okay. And this is really excellent question from Zainuddin. What if I did not find enough randomized controlled trials and I decided to include cohort studies in the meta-analysis? So it's like combination of cohort and randomized control.
Great question. As we said, the inclusion and exclusion criteria for your meta-analysis should be written down in advance, so you don't bias from your inclusion criteria. So if you decided to include all a randomized controlled trial from the beginning, I think you cannot combine observation and randomized controlled trial. But if you couldn't find enough randomized controlled trial and you wanted to include observational studies, you have to do this process again from the start. So you have to set up your inclusion criteria, you have to repeat your screening, you have to do everything from the start. And yes, you can. If you decided to include observation randomized controlled trial, yes, you can combine the data from both. But you may need to do an additional step, which is subgroup analysis. And we're going to learn about this with Aziz. Subgroup analysis for randomized controlled trial only, and subgroup analysis for observation studies only. And then you can compare, the outcomes in between the 2 designs.
And one last comment or maybe a request. Maybe it will be a good idea to have like blueprint, brief description about the steps, how to do meta-analysis, and what are the tools needed. Are these publicly available, like the Rhythman?
Rhythman, yes, sir. Rhythman is available and it's free. The CMA is not. But we can for the publication bias, the funnel plot, I can share an Excel sheet, build up Excel sheet that can do the same. Like they will give you the funnel plot and they will give you the Eagers test. So for the analysis part, probably they don't have to subscribe for any product.
Excellent. Okay, because I think PAMA is committed also to provide adequate resources for the people who participated in order to make sure this effort is successful. So I think if we can like have blueprint with links to the softwares, and that will be really fantastic.
Yeah, we can work on this, absolutely.
And Bilal is also agreeing with me. He's saying, could you give us some significant references? Yes, we will do that. If one study is making the group heterogeneous, can we exclude it? Wadi is asking.
We will answer this question with Aziz, but I can give you a hint. No, you cannot exclude it from the study. As I said, your inclusion criteria, they were set up from the start. So that's why we said that the inclusion exclusion criteria should be done in the first step. So you cannot just exclude based on the heterogeneity. You can do what is called sensitivity analysis, or you can do a subgroup analysis by excluding this study from that subgroup analysis, but you cannot exclude the study if you feel that it met the inclusion criteria of your research. No, you cannot just exclude it and ignore it. No.
Okay. And this is, I promise, the last question. No, I'm enjoying this, Mohammed. That's why I keep saying last question, and I find good question. If one study did not report baseline characteristic, like body mass index, for example, while the rest of the studies did that, what should I do? Should
That's
I
fine. That's fine.
So you have just to report number of studies that reported that variable, and they do not all have to have the same variable.
Yes, and actually, not all of the researchers and meta-analysis do the same that I do. Not all of them will combine all the data in one group. Some of meta-analysis, they will just report the numbers for each study. So they will have a big table, and then they will report males in every single included study. But I think this will make the table very busy and very hard to read it through. So this is the way that I do it. But you don't have to combine the data into single numbers. You don't have to test the homogeneity of your baseline characteristics. But I think this is very valid, and from my opinion, this is very important to be reported, because it does reflect your population, your study population. Everyone can go back and read the included studies, and they can know the number of patients that they included, or the number of male patients. But you are interested, they may be interested in your own numbers.
Okay, Mohammed, this was beyond fantastic. Thank you very much.
Thank you. My pleasure always, Dr. Turk.
I really appreciate that. And please make sure everybody to fill the attendance and evaluation. And I'll see you back next Saturday, inshallah.
Sure.
Thank you very much, everybody.
Thank you. Have a good one.